Hi everyone, today is day 9 of our uh, challenge for solving 30 machine learning projects in 30 days. So, the problem is about to modify CNN with pooling layers and visualize filters. And we will be using CIFAR 100 dataset. So, I'll go and use the same flow, go to the ChatGPT, use the same window, and see hey, it is day 8, not day 9, and the problem is modify signal pooling layers and visualize filters using CIFAR 100 data set. So let's see. Yes, so if you remember that we have used this CIFAR 10 data set for a couple of our problems for day 5 and day 8, and so we know what it looks like. So today we are going to explore the CIFAR 100 dataset, which is similar to CIFAR 10, only that now we have 100 classes instead of 10 classes. So it is going to be more challenging since we have more categories to deal with. Now we have to modify the convolutional neural network by adding more pooling layers. Earlier we had only two layers through max pooling. Now we'll add more layers and we'll see how it affects the performance. Also, we will visualize convolutional filter to understand what features the CNN is learning. So it says that pooling layers. By adding more pooling layers, we can further reduce the dimensions of feature maps, making the network more efficient and focusing on most important features. Okay, let's see what it is. So we know that we have a pooling layer. We saw it in just a second. Yes, we saw it in yesterday's problem. To understand the convolutional neural network, we saw that we have pooling layers. So we are going to add it to see its effect, how they're making the system more efficient by focusing on the most important features. Then we visualize the filters help, which helps us understand what kind of features the CNN is learning, such as edges, texture, more abstract shapes in deeper layer. Okay, we will see. When we will code, I guess I'll understand more. So let's start coding. I don't think we need to look back and understand it again because we have already done that in yesterday's problem. So let's come here and create a file for today's problem. Add it to the Git repository. Mention what the problem is about. Using CIFAR data set. Okay. What I can do, I cannot mention it here. I can just say CIFAR 100. Yeah. So let's start coding. So I'll say import the libraries. Import uh, tensor from TensorFlow keras models. Import sequential model. Layers, we have to import convolution, max pooling, flatten, dense, and dropout. We saw these layers yesterday, so we know about these layers, as in why do we use them and what do they do. And then we'll have to import the CIFAR 100 dataset from datasets package. So let's do that from TensorFlow keras layers, import convolutional 2D, max pooling 2D, dense, flatten, and dropout. Then from TensorFlow.keras models layers and what util dataset. Datasets import CIFAR 100. Then we have to import uh, tensorflow.keras.utils import to categorical. So we have to do some. I'll also see. I'm not confirmed. Maybe we have to convert it, handle the category data to convert them, uh, uh, apply one hot encoding or any other hot encoding. For that we are importing this one, so I'm not sure. I guess moving forward I'll see what it is used for. Then we have to import matplot.py plot as plt. Why? Because we'll have to visualize it using plotting graphs. Import numpy as an np. Also I want to see the data, how the data looks like, because this is the first time I'm exploring the CIF AR100 dataset. So I'll import pandas as pd. ChatGPT is not doing that, but we will do that. So first step is going to be now load the data. So load the data set is going to be into x train, y train. Then we have data set for validation, x validation. This is for the features and this is for the target. And now for validation, let's have y validation and load it from the CIFAR 100.load data. Once we do that, I want to see if there is any way to fetch it directly in the form of data frames. Okay, there is no way directly. Now once we are done, we will this normalize. Before normalizing, let's look at the data. So uh, let's create xtrain flat. Let's flat xtrain flat will be, let's reshape it into what is the size of the images. The size of the images are in the, so let's not rely on looking at the chat gpt. Let's do what, let's look at ourselves. Print xtrain dot shape. So in order to see how the data looks like, I have to convert it into data frame. For data, before converting it into data frame, I need to check the shape, because data frame accepts in 2D. I cannot pass on vectors more than 2D. So let's do what? Let's look at this, the shape of this training features. So it is downloading. It has not downloaded yet. Okay, it has downloaded, and the shape of our our training data looks like this. So let's flatten it. So if we will flatten it by x train flat will be x train dot reshape, and reshape into what would be the size, 32 into 32 into 3. And let's do what, and will be, this will be for columns. Let's do reverse, and then we will create a data frame. X train data frame will be pandas data frame, and create x, pass this x train data frame vector. And then let's print this x train data frame dot info, like how many columns does it have, what is the name of the columns. So it has 50,000 columns, and it has 30, oh, it has 50,000 columns, and then it has um, let's do what, let's see the data. Why does it has 50,000? Let's convert it. Let's print the shape of this new flat array. Let's mention this here. Does it change anything? Correct. So this is going to be as it is, and then the shape of the following vectors is going to change from 32 3 into 232 multiplied by 32 multiplied by 3, which is going to be 3072. Now we have 3072 columns, which is correct. I'm so sorry. So we have 3072 columns, and you can see how many. Now let's look at the information of this data frame. Clear the terminal and run it again. So now we have 3072 columns ranging from 0 to 3071. We have 50,000 entries ranging from 0 to 49999. And if you want to see the data, we can see the data of the first 5 rows using the head function. And when we see that the value ranges from 0 to, some values are 78, 93, 29, 59, 10, 4, 9, and 253, 253, 247, 239. So the value are in the range of 0 to 255. So we have to normalize that. Before I do that, I also want to see how the let's normalize that first. Normalize the data between 0 to 250, data from 0 to 255 to 0 to 1. So how we will do that? We will do that using this x train. Not, let's comment everything we have seen. We don't want to see it again. Let's say x train will be x train divided by 255.0 and then X validation also will have data something like this. Only the number of columns are going to be different. Sorry, the number of rows are going to be different. So exchange divided by 255.0. If you are not sure what I'm talking about, let me show you the shape of xval dot the validation data. Also, yeah, let's run the script, and you should be able to see the shape of the validation script is that everything is same, only that it has 10,000 images kept for the validation. uh, that is our unseen data. So yeah, it is also going to be same, that is why we are normalizing that as well, but here it should be x validation by 255.0. Now we are done with it. uh, so yes, I was correct. Now ChatGPT says to apply labels, to convert the labels to categorical format using one hot encoding using the categorical function. Before I do that, I need to see what the data actually looks like. The targets are looking like. Are they are they in the form of classes like airplane, dog, cat, or they are already in the form? They are already in the digit form. So let's look at let's look at the data. This target. So here we'll do what x, not x, y train. Flat will be y train dot flat. So it does provide a function called flat. We'll flat it and then create a x not x y train. Data frame will be pandas dot. We will not have data frame. Why? Because if you see, let's do what, let's before doing that, let's visualize the data. Let's look at the shape of the of our target variables. So if I look at the shape of our target variables, and they look like this: 50,000 on one dimensional, 10,000 one dimensional. So they are in already in the one dimensional, okay, and 50,000 kept for the validation training, and 10,000 kept uh, for the validation. Now if I uncomment this, here I know this will convert it into, let's do what, print the shape of y train flat and comment this. Let's keep on commenting this. Sorry, uncomment that. So it is in the numpy format, okay. So it will have of 0 point into 2 this. So we'll do what, now pass this flatten into our uncommented series y train flatten, and then we will simply look at the data as in visualize the data. So the data is already in the form of 0 to 0 to what, 0 to 29, 0 to 100, I sorry, 0 to 100, 0 to 99. So we do not have to apply uh, one hot encoding using two categorical function, because it is already in the form of digits. So we'll this and same thing with y underscore value. So you will skip that step, and you will also remove the package that we have imported. Now we will do what, we will build the model. So after doing all the pre-processing, here we are doing what, we are doing pre-processing. After doing all the pre-processing, let's build the model. The model is going to be a sequential model, and let's add the first convolutional layer. So model dot add dot convolutional. How many neurons we have? We have 32 neurons we start with. What is the size of the filter or say kernel? We have already explored what it is. 3 by 3. Activation function is rectified linear unit and input shape is 32 32 3. So it is going to be 32 filters. How many filters you want? 32. What is the shape of the filters? 3 by 3, or we say kernel size. Then the activation function is rectified linear unit, and then we have the input shape is going to be extreme dot shape. Here start from 1 and end it to anything, so that will print 32 32 3. And then we will add the pooling layer. So pooling layer is max pooling 2D. Here we will add max pooling 2D of size 2, which is to extract the so it will extract the features, right? Now we apply pooling. Why? Because we want to now we want to extract the important features as in um yeah, the from 2 by 2 grid, get the pixel value that has the maximum value, that one. So then we'll have second convolutional layer. We have model dot add. Second convolution layer is convolution 2D. 32. Sorry, let's increase the size. Now we want to emphasize. So we are adding how many convolution layers? 3 today, and the size is going to be 3 by 3. Activation function is rectified linear unit, and model dot add the pooling, max pooling of size 2 by 2. And we have third convolutional layer, model dot add convolutional 2D. Size will increase to 128, and the kernel size is 3 by 3, and not the size, filters actually. Activation function is rectified linear unit. Rectified linear unit, model dot add max 2D polling 2D. The size of our polling strides. Now we will flatten them. Once we have added the layers, it has extracted everything. We want to add a flattening layer. Why? Because neural network cannot be trained on the multiple type vector, multi-dimensional vector. So we need to convert them into 1D vector. Also, yeah, 1D vector. Also, so this will convert it into a list of the important features. And then we will do what? And after flattening it into a list of important features, we add the last layer, which is a fully connected layer. Which is fully connected layer. If you remember, we have learned it that the fully connected layer is to connect the edges and tell what the image is about, like predict what the image is about. So we will do what? Add the last layer, which is fully connected layer. So fully connected layer is a dense layer of the size is 100, because we have to predict No, fully connected layer. This is not the size. One of size 128, and the activation function is rectified linear unit. Then we will add a dropout layer because you want to prevent the overfitting. Let's drop out 50% of the data of the neurons, randomly 50% of the neuron. Then we'll have the output layer. We'll have the output layer. How many neurons should we have in our output layer? 100, because each neuron will represent the. This is Sankina. Yes, each neuron will represent the category 0 to 99, and so the activation function is going to be softmax, because you want to do what it will print. It will output each neuron as the value of each neuron as the probability, and whichever will have the probability, maximum probability, that will be the output for that image. Predicted output for that image, like 0 1 2 3. Let's say the ninth neuron will have the maximum probability, so 9 is the category 9 is the output for this this image input image. Now, one more thing, the sum of the all the neurons probability is going to be 1 from this activation function. Once we do that, we need to compile the model. um, so model dot compile. uh, how what functions we want? First we need to mention the optimizer. So the optimizer is going to be the one that we have been using mostly, but we have explored other optimizers in our day 5 problems, but we do know why we are using this atom. Then we have, how do we calculate the loss? We are going to calculate the loss using sparse categorical cross entropy. Why? Because the digits are in so the output is in the form of 0 to 99, so that is why sparse. We are, it is a binary classification, that is why categorical cross entropy. Then we have to mention how do we calculate the performance. We do that on the basis of accuracy of the model. This the ChatGPT is saying to use categorical cross entropy, but it will throw error. That's why we are going with that. Yesterday it was like that only. We were using categorical cross entropy, and we saw that it was the reason of the error. So yes, and we had to add this parse. Once done. Let's now what train the model. We'll do what model dot fit. Here we mentioned this is the training data. This is the target. The validation data is x validation, y validation, and then epochs. How many epochs ChatGPT is saying to run? It is saying to run 10 epochs of past 64 size. But yesterday we saw that when we increase the epochs from 10 to 20, we saw increase in the performance. The model was doing really good, but we will go with 10. And then we will say, okay, the model is performing this much on 10, and then yeah, if required, we will increase the epochs. If not, we would have understood that on increasing the epochs and decreasing the batch size, the model becomes training becomes slow, but the model performs really good. But for the sake of the video, we'll stick to this. To keep it short, we'll stick to this. Now verbose is going to 1 because we do want to see whatever the model is doing for each iteration on the terminal. So that all is needed. Yes. Now the final step is visualize the performance. How do we visualize? First, by plotting the loss. So for that, first we will plot a graph of size 10 is to 7. Sorry, 10 is to 7. Not print, plt dot plot. Let's plot a curve. Before that, let's store whatever the model is training into a variable called history. And before that, let's do what? Convert this history into a data frame so that it becomes easier for us to plot it. So panda dot data frame history dot history. Okay, once done, we will plot it using the history data frame. Here the loss is for our training data is saved in the loss column, so we will do that and mention the label as training loss, and we have a typo, and plot the history data frame for. Now we want to see the loss for our validation data, so using the column validation loss, the label is going to be validation loss, and then we will do what? Plot the mention what is the x label for our x. It is going to be epochs x axis. What is the label going to be for our y axis? It is going to be loss. We are looking at the loss. We want to see what each line represents is used for, so we will do what? Use this legend function. Then we want to mention the title of the, what is that going to be the title of the plot? It is going to be training and validation loss, and we have the same title. And now let's simply show the plot. Now we want to plot for accuracy. So wherever you see accuracy loss, just replace it with the accuracy, and the columns are going to be accuracy, and the validation, well, for validation it is going to be val underscore accuracy. We are pretty much done with our code. Let's clear the terminal and run the file. So it is training. We do not have any error. That is really good. So on an average, it is taking 10 seconds to train one for one epoch. Yeah, it is taking 13 seconds for an epoch. It is starting with a loss of training loss of 4.2, accuracy of 0.05, which is too bad. Validation loss of 3.75, and accuracy is of 13%. So let's wait for it to complete the 10 iterations, and then we will go through it. Okay, there is one more layer that we have not step that we had not added. We need to visualize the filters. So for visualizing, visualize filters helps understand what kind of features, edges, colors, texture the model is learning. Okay, so we'll go to get the weights of the first convolution layer. So we'll go with model dot layer 0. So model dot layers 0 axis is the first convolution layer, first layer. Now we get the weights from the first layer and store it in the filters and biases. we extract the weights filters, that is the weights and biases for the filters, as in the filters and the biases. Filters are the weights from the first layer. We normalize it, normalize filter values to 0 1 for visualization. um, so we do this normalization. Once done, plotting the filters, number of filters to visualize, not this. Okay, training is looking good. Here also it's looking good. It stopped at accuracy 29% accuracy, for validation 33, very bad. So I'll go and increase it to maybe epochs will be 20, batch size will be 32. Now it will perform better. But before doing that, now before running it again, let's complete the problem by adding the step 6, which is to visualize. So it says get the filters and biases from the first layer, normalize it, and then plot the filters. So number of filters to visualize, we want 6 filters to visualize. Fig and x's. Let's understand what. Okay. So we are using matplotlib to plot the first few filters. The filter will show patterns and the patterns the network looks for, in such as edges and specific color. So it takes the axis and the figure plot using the matplot library. Goes from 0 to 6 number of filters. Get the filters. It is like get all the filters up to this, and we are going in the range of 3 because we have RGB, and then we get the axis, and then we show it. I don't understand much of it, but let's follow it. I do understand now. Using this, we are plotting the graph to visualize it. Now let's do the last step is to visualize filters of the first convolutional layer. So for that, forget the first layer as model dot layers, first convolution layer. Then we get the filters and biases from this first layer using get weights. I do want to see this first layer. I also want to see this filters and print biases, and before um, and then we need to normalize filter values to 0 for visualization. Nor the filter values for is to 0 to 1 for visualization. Let's go ahead with what it says, and then we will understand it. Filters minimum is going to be, okay, so let's first get the filters minimums and maximum. Filters dot min is the filters minimum, and filters max is going to be stored into the filter maximum value. Now filters will be set to filters, let's numerator will be filters minus filters min, and will be filters max minus filters min. Yes, Now we are converting it into 0 to 1. So let's say we have maximum value of filters, let's say 0. I want to understand what we are doing. The maximum value is 255. Minimum value is 0. Maximum value is 250. Minimum value is 1. Maximum value is 255. And now we will convert it into filters. First value is, let's say, 34. So it will look like 34 minus minimum will always be a positive number, divided by maximum minus minimum is the range 254. So if we do that, let's do what? So it is going to be 33 minus 254, so 255. It will always be, yes, it will always be lesser than 1. Why? Because let's say we have a number called 255. So this is coming in the range of 0.12. So this is coming in the range of 0 to 1. But let's say we have a maximum number 255. A number cannot be greater than maximum because we have seen it. So for 255 is going to be 255 minus the minimum divided by 255. For even 255, on decreasing it, it cannot be greater than 255. So it cannot be greater than what? It cannot be greater than 1. So it is going to be 254. Let's say our value start with 0. In that case, it is going to be 0. So is it understood? If it is going to be 0, let's say our value start, the minimum value is 0. In that case, it is going to be 255 minus 0 is 255 divided by 255. So the value will be 1. So it cannot be greater than 1. That is why it will always be in the range of 1. And for minimum, for the pixel value with minimum values, the numerator becomes 0 because minimum minus minimum same values become 0 and the value will be 0. So it will always come in the range of 0 to 1. That's why we are doing this. Let's come back here, close it and come back here. Now we will do what? Plot the filters. So get the number, how many filters you want to plot. We want to plot number of filters. Filters is going to be 6. Number of filters, how many number of filters you want? 6. This is the figure and the axis. So we'll plot PLT subplots. Here we mentioned the number of rows, number of columns, and everything. So number of rows is 1, number of columns will be number of filters, and then the size is going to be number of rows, number of figure size is going to be 20 to 5. Once done, now plotting it will go from filter number in number of filters कितने, how many we have an index and number of filters, range of number of filters, and then first we'll do get the filters. We'll do what? F is equal to filters will be filters will be, sorry, let me close it. filters will be filters will be .I. Okay, so it will be dot dot. Let's run it and then I'm going to ask it from the chat GPT what it means. Index. Okay, .I. Once we have got the filters, plot each channel separately. We need to plot each channel separately. We will do what? For JN. Now if it is channels, we'll say channel. CHA Chanel. It is Chanel. Channel in filters. We have three channels, right? For we have three channels. RGB channel. Once we have got the channel, we'll say axis will be axis. Get the channel axis. Then x dot I am sure get the filter channel and CMAP will be give random colors and axis of done. We'll do what? Plot it. Done. We have plotted all the channels and subtitle filters of the first convolution layer. Filters of the first convolutional layers, and then simply show it. Let's clear it and run it. Meanwhile, it is running because we have increased the epochs from 10 to 100, 10 to 20, and also decrease the batch size, so it is going to take some time. Meanwhile, it is doing that. Let's do what? Let's understand this. I say, can you please explain each line of this piece, not piece, code snippet of step 6. So yes, so and the goal is to extract the features, okay, from the first. Filters on convolutional layers are used to extract features from the input layers. Yes, we know that. In this snippet, we want to visualize the learned filters from the first convolution layer. These filters represent patterns that the network has learned, such as edges or texture. Okay, we want to see that. So get we first get the first layer. We saw that, and we get the filters and the bias. This represents the first layer. So the model dot layers contains a list of is a list containing all the layers in the CNN model. By using model.layers 0, we grab the first layer, which is usually a convolutional 2D layer in this CNN. Then we get filters and biases. We retrieve the weights of this layer, which is the filters, and the biases of the convolution layer. Filters and biases that the convolution layer has learned. Filters represents the kernels that will convolve over the input image. Okay, biases are the additional parameters that changes these filters. Then for this we have understood that. Okay, now plotting the figure. And why are we doing normalization? This is a really good line. We are doing it because it normalization is important for visualization, because it makes all the values lie in the same range, which makes plotting okay. So we are making sure that the lines are lying in the range of 0 to 1, which becomes easier for plotting, visualizing. Okay, because they will lie in the same range. Okay, and we have applied min max normalization. So this is what this is simply min max normalization. Now after doing that, we mention how many filters we want to visualize. 6 filters. Then what are we doing with this line? We create a grid of subplots with one row, and how many columns in row we want? We create a subplot of with one row and these many columns. This is the size we saw that. And imagining it like setting up a small six small picture frames side by side, where each frame will contain a different picture of the filters to understand. Okay, so we want to create subplots of one row and 6 columns, 6 sub filters, which means 6 small pictures. They are setting up it side by side. Okay, it will become easier to understand what filters looks like for uh, in the input image. And then we loop to visualize each filter. Then we this loop goes through each of the 6 filters that we want to visualize. Okay, then what this it selects the ith filter. Which filter we want to select? We want to select the ith filter. Which filter? First filter, second filter, third filter, fifth filter, fourth filter, fifth ith filter. And the filter have a shape of filter height, filter width, number of channels, and number of filters. So we are going with take the whatever filter height not mentioned, filter width, number of channels not mentioned, but we do mention the number of filters. So here what we are doing here, it is select the ith filter. So here select the ith filter, and it is filter height, width. Let's minimize it for now, understand it first. Filter height, width, channel, but we specify number of filter. And then we go by specifying we are selecting the ith filter to visualize. Each filter has 3 channels. Okay, we are selecting a filter. Now each filter have 3 channels. RGB for RGB. Okay, now we are selecting those channels RGB, red, green, blue. Each filter in a conventional layer has 3 channels because the input images are in the RGB range, 3 channels. Good. And now I want to understand what these 3 lines are doing. The axis X, that is axis I, is the collection of subplots created earlier. Okay, so it is the collection of subplots created earlier. Axis I, if you remember, this was the axis of the subplots created earlier. So you want to see okay, the current X. So we get the channel from this one, and then we show that. Okay, is used to select which subplot to plot on the current filter on. Okay, then X dot I am sure you want to show that filter, where selects the jth channel on the filter. Uh, I am sure is used to display the filter as an image show. Okay, specifies the filter color map to which use the present different values. Okay, so it is a common choice for visualizing different values. Okay, this function is used to, so we are getting the access, that is the subplot of access of the subplots from the main figure, and then we see we get the current channel of that axis, Now we show it as in the form of image, and then using this function, and then we mention what image we want. This image, this color, I mean it is like picks up the multiple colors automatically, and then we want to show off. So we want to turn off the access to make the visualization. Okay, we want to turn off the access because we want to make the visualization clear. Focusing only on the filters content without extra number of greatness. Okay, we want to focus only on the number of filters without showing everything. So I would have turned it on to visualize, to see what it is used for. And yes, I understand that. So in just to go through it again, what we are doing, we are getting the first layer and the weights and the filters, and then we apply min max normalization because it becomes easier, because the range is shortened now. It becomes easier for plotting and visualization. Then we mention how many filters you want to see, 6 filters. Then we plot the graph, we get the excess of the subplots and the figure. Then we go to each filter, we get the filter by mentioning the width, height, width, filter width, filter height, number of channels, and the number of filters by mentioning the current filter. And then we go through each channel. Generally, there are 3 channels: RGB for red, blue, green color, green, blue color. And then we plot that channel using the IMShow function. First, we get it using the axis in the subplot, and then we show it using the IMShow function, the image. And then I would have turned it on, but for now we are turning off because we want to see the clean image, and then we show it. Now we have understood it. Let's see, the model is complete, has completed the 20 epochs. It started with 4.1, 4.2 accuracy loss and 0.055% of accuracy. On validation data, the accuracy is 13%, and the loss was started with how many? With 3.7, and then it closed at loss 2.38. It did it increase? No, it decreased for 4.3. Accuracy is 36%. For validation, accuracy is 36%, similar, and the loss is also similar. If you remember, last time we ran for 10 epochs, the accuracy was 29%, so it is still better. Now it was showing me a plot. So this is how the plot looks like. It can further go good if we, hyper tune our parameters, see which parameters combinations are working. But let's go for with this for now. If you are clueless what I'm talking about, you can, I'm talking about this that we have explored in the DCM, that we can configure, find out which combinations of parameters are good for for our performance, for our model. We can get that by hyper tuning. So we could have applied that if we want to, make our optimize the performance of our model. So this is how the accuracy is going. It is going steadily increasing. For validation also it is steadily increasing. Let's take this screenshot and close it. And this is the 3 images. So okay, so they look like this. So this is the figure 1. Okay, and we did not see the rest of the figures, right? Oh, I wanted to see all the figures actually. Strange. It did not show me all the figures. It should have. I guess I mentioned the PLT show in the last. I should have mentioned under the. Hmm. Okay. I did not see for all the filters. I saw only for the first filter. But yeah, the filters look like this. First layer looks like this. Then the filters look like this. And this is the bias. These are the filters. These are the filters, and this is, I guess, is the first layer filter. See, this is what you printed, and we want to print this thing. So yeah, the layer was looking like that only. If I would have run like next time, maybe I can come here and show you. Yes, filters of the first conversation layer looks like this. This is these are all the filters. Oh, nice. I don't understand much, but yeah, but cool. Let me let me let me do what? Trim it, crop it, save it, and pass it to ChatGPT. I have the paid membership, so why not use it completely? And this is how it looks. How can you help me understand it? We will see a row of six subplots. Each line represents filters. We have six subplots filters in a single row, but it looks like okay. The first three look are completely colored. The last three are blank, empty. Okay, so we have six images. Each subplot is meant to represent a filter of the first convolution layer. Okay, these filters are 3D tensor because they operate on color images. Therefore, each filter is composed of three 2D matrices for each channel. The visualization is attempting to show each channel the filter. So these are all six. 8, 2, 3, 4, 5, 6. Okay, and the first are colored and the rest three are empty. Hmm. Okay, so the loop might not have correctly plotted for some of the filters. Okay, the filters value for those particular filters could be mostly zero returning. Okay, that is why mostly these values are zero. That is why it is returning blank. Okay, interpretation of filters that are generated nicely is that the first convolution layer, the filters are usually look for the basic features like edges, colors, and simple patterns. Each of the colorful square is a 2D slice of the 3D filters representing how it looks at each channel: red, green, blue. This red, green, and blue. And then for example, if a filter has more green color, it might be confusing on green areas of the image. So our filter has more green colors, which means it might be confusing on the green areas of the image. Okay, and then it says that for fixing the last three filters, what we can do. So it says only plot the first channel for simplicity. What we can do, we can plot the first channel for simplicity. I'll go and maybe mention the first channel for simplicity. Okay, I'll keep it as it is because the video will become longer now. Maybe what I can do, I can close it for now, and I'll go and change it. Okay, and run it again. Let's learn it again. I mean, this is for me, not for everyone, right? Sorry, I should have changed it to I. Now let's run it again. I had a problem with my code. Let's run it again. It will take some time. I guess it will take 2-3 minutes. So you might have to fast forward it to the 2-3 minutes. But I'll wait. So we are almost on the last epoch. So we have already looked at these things. Yes, now we see all the three, six, six layers. Uh, this is good, and yeah, we understood that what they represent. They represent the basic filters like features like edges, colors, and simple patterns. They are the representation of the weights in the filter. The colorful square that we saw represents the weights in the filters. Okay, this is the similar weight, I guess. The color corresponds to the weights. The colors correspond to the weights of the filter at different position. But the brightened colors represent high weights and the dark represents low weight. Okay, so I'll go. This is very good line. I'll mention it here. So what it is, the colorful names we saw uh, here are the weights. The darker are the higher weights. The bright colors are high weights. The dark colors are low weights. So dark colors are low weight. So bright. This is high weight. This is high weight. This is high weight. It has high weight. This is lowest weight. Lower weight. Low weight. Okay, understood. Makes sense. So yeah, this we see the filters from the first convolution layer, and it is really good. Now let's go commit the code. We are almost done with today's problem. The 9 message will be add code for D9 problem. We have added it. Let's push it to our main class, the main branch. Let's see it here. If we see the code, we do see the code. So yeah, we are done with today's problem. It is really good to see how the filters from the first convolution layer looks like. Now we'll come back tomorrow and solve our first problem. I mean, yeah, we'll I guess let's park it for tomorrow only. So yeah, thank you very much, and yep.